Hello everyone, my name is Paras Palani and today we are going to discuss the integration of this function ln 1 plus sin x to the power of 4 dx over sin square x, and we integrate it from 0 to pi. Okay, so to solve this integral, first of all we need to know some things. Okay, we need to know what is natural logarithm of a complex number, any general complex number a plus b iota. So ln of a plus b iota is nothing else but ln of root of a squared plus b squared plus iota tan inverse of b over a. Okay, this is a standard result in the complex numbers, that ln of any general complex number a plus b iota is ln of root of a squared plus b squared plus iota tan inverse of b over a. Okay. Now, if we only consider real part of ln of a plus b iota, it would be ln of root of a squared plus b squared. And we know a property of natural logarithm that this power can go out. So this power 1 by 2 goes out over here, and when it goes to LHS, it becomes 2 times real part of ln of a plus b iota is ln of a squared plus b squared. Got it? Now, you see the expression which is given to us. It's ln of 1 plus sin x to the power of 4. Okay. We can write 1 over here as 1 squared and sin to the power 4 of x as sin square x whole square. Okay. So using this expression over here, we can write that this is 2 times real part of ln of 1 plus iota sin squared x. Why? Because b over here corresponds to sin squared of x and a over here corresponds to 1. So 1 came over here and iota b, that is sin squared of x. Okay. So in all, earlier we need to calculate I, which was integral 0 to pi ln of 1 plus sin to the power 4x dx over sin squared x. But now our integral transforms to 2 times real part of 0 to pi ln of 1 plus iota sin square x dx over sin square of x. Okay, now we'll solve this particular integral by Feynman technique. How will we? We'll parameterize the given function over here. So we'll define a particular function f of t as integral 0 to pi ln of 1 plus t sin squared x divided by sin squared of x dx. Pretty much fine. What did we do? Over here we had a particular function. Okay, we said let us say that this particular function is f of t, where we replace I with t. So we parameterize this entire function as this, like f of t is 0 to pi ln of 1 plus t sin squared x upon sin squared x dx. So we parameterize this particular expression into this particular function. Okay, now what we'll do is, like, what would be our final answer? It would be I would be 2 times real part of f of I. And also one more important thing to note over here is that if we put t over here equal to 0, if we put t equal to 0, we'll get ln of 1 in the numerator, which is 0, and integral of 0 over any interval is 0, so f of 0 must be 0. So if we put t equal to 0 over here, we get numerator as 0, and so it produces 0. So f of 0 is 0 is a standard result from the which we can obtain from this parameterized function, and the integral that we need to calculate right now is 2 times real part of f of I. That is, we replace t with I, and whatever this quantity is, that is the answer for our integral. Now what we do is we differentiate this particular function that we took. So we differentiate this f of t with respect to t, which is a standard practice of Feynman technique. We differentiate the function that we assume with respect to the parameter. So what would be f prime of t? That is differentiation of this function with respect to t. Would be, say, we'll use Leibniz rule over here. And what Leibniz rule says is that the differential goes inside plus upper limit substituted, differentiation of upper limit, which goes to 0 because differentiation of upper limit with respect to t is 0 because pi is a constant, minus lower limit substituted and differentiation of the lower limit with respect to t. Now differentiation of 0 with respect to t is again 0. So what we get is that according to limits rule, we just get that the differential sign just goes inside. And we are differentiating with respect to t, so sin squared of x remains constant. And ln of 1 plus t sin squared x differentiated will give us 1 over 1 plus t sin squared x. And then using the chain rule, we get the differentiation of this is sin squared of x, and sin squared of x will get cancelled out to give us this expression. So now the f prime of t that we calculated, that is differentiation of f, the parameter's function with respect to the parameter t, is integral 0 to pi 1 over 1 plus t sin squared x dx. Now we can find this particular integral that we obtained over here using the integral of a standard general function g of x. We define a general function g of x as integral 0 to pi 1 over a plus b sin squared of x dx. Okay. Now if we are able to find the value of this integral, the value of the gx over here, which is integral 0 to pi 1 over a plus b sin squared of x dx, if we're able to find this particular integral, and if we substitute a over here as 1 and b over here as t, then we'll get our f prime of t. Okay, so we need to find f prime of t, which is this integral. That could be that could be found if we are able to find the integral of this general function. Now clearly, if you see that if we put minus of x in place of x, we get sin square of x again. So what I mean is that this particular integrand is even. Because this particular integrand is even, therefore we can use King's rule. So basically, instead of integrating it from 0 to pi, we could just integrate it from 0 to pi by 2 and double it up. So g of x, instead of being from 0 to pi 1 over a plus b sin squared of x dx, it would be 2 times of 0 to pi by 2 1 over a plus b sin squared of x dx. Now we know that sin square of x is 1 minus cos 2x, because we know that cos 2x can be represented as 1 minus 2 sin square of x. Okay, there's a standard identity of cos 2x. There are 3 standard identities of cos 2x, that is cos square x minus sin square x, 2 cos square x minus 1, and 1 minus 2 sin square of x. So we use the third identity that cos of 2x is 1 minus 2 sin square of x. Using this property, if we replace sin square of x over here, we get this. Now if we take 2 over here, we get 2a plus b times 1 minus cos 2x, and 2 goes in numerator. So we get 2 integral 0 to pi by 2 over 2a plus b times 1 minus cos 2x dx. Okay. Now that we have got this, now what do is we let c to be 2a plus b. Now starts a chain of substitutions and manipulation that we do to find this particular integral of this general function. What we do is, over here you can see 2a plus b appearing, although it's not explicitly appearing, but we see 2a plus b appearing. We assume c to be 2a plus b. So if c is 2a plus b, then 2a would be c minus b. And we see b minus b cos 2x over here. b and minus b gets cancelled out to give us c minus b cos 2x. So our integral turns to so you can see over here, here's a 2 and here's one more 2. So this and this together becomes 4. So our integral becomes integral 0 to pi by 2 4 times dx over c minus b cos 2x. Okay. Now let's substitute one more thing. So let u to be 2x. Okay. Why did we do that? We substituted 2x over here to be equal to u so as to make integration easy. So we substitute u to be 2x, so du would become 2dx. Now if x is pi by 2, u would become pi, and if x is 0, u would become 0. So our integral g of x now transforms to, because we have dx, so dx could be replaced by du by 2, and 4 is outside, so 4 and 2 gets cancelled out to produce 2 over here. So we have 0 to pi, 2 times 0 to pi du over c minus b cos u. Okay. Now that we have obtained this, again we do a new transformation. We know a specific formula of cos u in terms of tan u by 2, and that transformation would be useful to solve this integral. So what we do is we assume t to be tan u by 2. In that case, dt by du would be half of sec square u by 2. Oh, there's a mistake over here. Okay, I can maybe overwrite that this is sec. Okay, this is sec. So like if we have like t is tan u by 2, then dt by du would be half of sec square u by 2. How did that happen? So basically differentiation of tan is sec squared. So tan t differentiation would be sec squared. So tan x differentiation would be sec squared of x, and then x would be x, that is u by 2 over here, would that if differentiated would give us 1 by 2. So simple chain rule. So dt by du would be half sec squared of u by 2. Now we know an identity that sec squared of x minus tan squared of x gives us 1. So sec squared of x could be written as 1 plus tan squared of x. So sec squared of u by 2 is replaced as 1 plus tan squared of u by 2 over here. So get half of 1 plus tan squared of u by 2. And we know that tan of u by 2 is t by the substitution that we assumed. So we get 1 by 2 of 1 plus t squared. Also, the now using this and this, we get du to be equal to 2 over 1 plus t squared dt. And then if we calculate limit, if u was 0, t would be 0. Simple, because if you put 0 over here, tan of 0 is 0. And if u is pi, tan of pi by 2 is t is infinity. It's a standard result. So if u is pi, then tan of u by 2 is infinity, that is t is infinity. So now we do the substitution of cos of u, that is we replace cos of u with 1 minus tan squared of u by 2 upon 1 plus tan squared of u by 2, and tan of u by 2 is t, so we get 1 minus t squared over 1 plus t squared. And now gx is 2 times integral 0 to pi 1 over c minus b cos u du. We replace this u and we substitute it with d. So du becomes 2 over 1 plus t squared dt, and cos of u becomes 1 minus t squared upon 1 plus t squared, and it is c minus b, and over we have 2. Now if we do some mathematical manipulation, we get c times 1 plus t squared minus b times 1 minus t squared, and 1 plus t squared goes in numerator, and in numerator it cancels out with the 1 plus t squared in the denominator of the 2, and then we get 2 times 2 over here becomes 4, or 4 integral 0 to infinity. The limits changed as I've discussed before, and it's 4 times 0 to infinity, 4 integral 0 to infinity 1 over c minus b plus c plus bt squared. How did I get that? So you see over here c minus b and c plus bt squared. Okay, so we get this. And this, if we take c minus b as common over here, we get 4 over c minus b integral 0 to infinity 1 over 1 plus c plus b over c minus bt squared dt. Now if we substitute c plus b over c minus b as k squared, we get k to be equal to root of c plus b over c minus b. So this is our substitution. We substitute k to be root of c plus b over c minus b, and in that case we get the integral to be equal to 0 to infinity 1 over 1 plus k square t square dt, and that is a standard result, that is 1 over k tan inverse of kt, and putting limit from 0 to infinity we get it to be equal to pi by 2k. Now what was k? K was root of c plus b over c minus b, so it becomes pi by 2 root of c plus b over c minus b. Now g of x was 4 over c minus b integral 0 to infinity 1 over 1 plus k square t square dt. Now we found out that this particular integral is pi by 2 root of c plus b over c minus b, and 4 over c plus c minus b remains over here. So it's like a root of c minus b cancels out root of c minus b, and then when we combine it, it becomes root of c squared minus b squared, and 2 cancels out a 2 from the 4, so we get 2 pi in the numerator. Now the integral 0 to pi 1 over c minus b cos u du is 2 pi over root of c squared minus b squared. Got it? Yeah. Now if we replace c with 2a plus b back over here with some mathematical manipulation, we get pi over root of a times a plus b. So we got the integral of a general function 0 to pi 1 over a plus b sine square of x dx to be equal to pi over root of a times a plus b. Now if we replace a with 1 and b with t, we get f dash of t, which was integral of 0 to pi 1 over 1 plus t squared t sine squared of x, and this particular integral is pi over root of 1 plus t. Like just put a to be 1 and b to be t. Got it? Now if we have f prime of t as pi over root of 1 plus t, then f of t would be just the integral of it. And how will we integrate it? It's simple, it's just u substitution. So like it's a standard result. So you can see like minus 1 over 2, like the 1 plus t if put in numerator would be 1 plus t to the power of minus 1 by 2. It integrated with respect to t gives us 2 root of 1 plus t pi. So we got this over here. So f of t integrated, so f prime of t integrated with respect to t would be f of t, which is 2 pi root of 1 plus t plus c. Now this was an indefinite integral because like you see there's no limit over f prime of t. So we get a constant of integration, and we know that f of 0 is 0, as we have discussed earlier. If we put 0 over here, we get 2 pi plus c, like it just becomes root of 1, which is 1. So we get 2 pi plus c. So f of 0 is 2 pi plus c over here, but that must be 0. So c becomes minus 2 pi. So we get f of t as 2 pi root of 1 plus t minus 2 pi. Got it. Now, what was our initial integral? It was 2 times real part of f of I. What was that? It was 2 times real part of 2 pi root of 1 plus I minus 2 pi. How did I get that? Okay, let me explain it to you. So what is f of I over here? What is f of t over here? It's 2 pi root of 1 plus t minus 2 pi. Just put I over here. You will get 2 pi root of 1 plus I minus 2 pi. Got it? Now, to go on further, first we need to understand what is meant by root of a complex number. But first let's simplify this. So what we are getting is 2 times 2 pi real part of root of 1 plus I minus 4 pi. That is 4 pi real part of root of 1 plus I minus 1. Now. What is 1 plus I actually? It's nothing else but root of 1 squared plus 1 squared. Like 1 plus I is at a root 2 distance from the origin, e to the power iota tan inverse of 1 over 1. Okay. Why? One is the y and one is the x. So 1 over 1. So we get root 2 of e to the power iota pi by 4. So 1 plus iota when represented in polar form gives us root 2 e to the power iota pi by 4. Now what is a root of a general polar representation of a complex number? It is root of r e to the power iota theta over 2 plus k pi, where k can either be 0 or it could be 1. It's a standard result. Now, what would be root of 1 plus iota? 1 plus iota represented in polar form is root 2 e to the power iota pi by 4. So it would be 2 to the power 1 by 4 e to the power iota pi by 8 if k is 0, and 2 to the power 1 by 4 e to the power iota 9 pi by 8 if k is 1. Now we know that e to the power iota theta is cos theta plus I sin theta. That's the Euler representation. So e to the power iota pi by 8 would be cos pi by 8 plus iota sin pi by 8. And e to the power iota 9 pi by 8 would be cos 9 pi by 8 plus iota sin 9 pi by 8. Now we know that cos pi by 8 is root of 2 plus root 2 over 2. And sin pi by 8 is root of 2 minus root 2 by 2. And because we know that 9 pi by 8 is just pi plus pi by 8, so cos 9 pi by 8 is minus cos pi by 8 and sin 9 pi by 8 is minus sin pi by 8. Just the simple ASTC rule of trigonometry. Now root of 1 plus iota in that case would be the 2 raised to the power of 1 by 4, and like first we take these two, cos pi by 8 plus I sin pi by 8, which is this, and 2 to the power 1 by 4 cos pi by 8 plus minus cos 9 pi by 8 plus iota sin 9 pi by 8, which is minus cos pi by 8 plus minus iota sin pi by 8, which is we just take the minus sign out, we get this. So what is real part of root of 1 plus iota? Although 1 is coming over here, but the real part over here is 2 to the power 1 by 4 over 2 root of 2 plus root 2. If we take this 2 to the power 1 by 4 inside, we get root of, it becomes root 2 when it goes inside, so it becomes 2 root 2 plus 2. So you get root of 2 root 2 plus 2 over 2. Now our integral was 4 pi real part of f of I minus 1. So it was 4 pi root of 2 plus 2 root 2 over 2 minus 1, and 2 now, like if we take 2 over there, and if we cancel out 1 2 from with the 4, we get 2 pi root of 2 plus 2 root 2 minus 2. So finally our final result is that I is the integral of 0 to pi, the integral of integrate ln 1 plus sin x to the power 4 dx over sin squared x over the interval 0 to pi is 2 pi root of 2 plus 2 root 2 minus 2. So that was the complete explanation. Thank you.